Yeah, welcome back. So we're talking about the Big Bang, the beginning of the universe. We've seen several pieces of evidence, two pieces of evidence now that it was there. Let's think about history of the universe, what it actually was like, what stages it went through in its course to being where it is now. And let's begin with the question T equals 0. The Big Bang, what were conditions like? Well, if you look at the previous plot that we had, or is it this one? If you extract, I mean, this is a log plot, so it will never go to 0. We'll just get smaller and smaller and smaller, and the temperature will just get higher and higher and higher. If you extrapolate to T equals 0, the temperature goes to infinity. It gets infinite. We don't understand how physics works at an infinite temperature, and there's something that breaks down with the model then. We don't really understand it. We understand what happens, how the universe acts from about here onward, but that's about it, interestingly. Interestingly, at T equals 0, what were conditions like? Well, we don't know. Infinite, maybe? Question mark. What does that look like? How does that work? How does physics behave? We don't really know. But we know lots of things about what the universe did look like. This is a very busy plot um, that's actually an animation. This is sort of a summary of it. I'm going to be showing you this animation, but if you want to come back and look at this, maybe you can read this, maybe you can't. I'll be going through all of it anyway, though. Let's take a look at this animation, and I will share this with you. There it is. Here it is. Okay, hopefully you're seeing this now. So this is, again, I've got a slider bar on the left-hand side now, and I've got a thermometer on the right-hand side. And so I'm at present day. The temperature is 3 Kelvin. Humans observe the cosmos. This is where we are at in the universe. As I slide this down, we're going earlier and earlier in the universe, and we'll see what conditions are like as we go. I'm going to go down first, talk about what's happening here, and then we'll talk about moving from the beginning and moving up. So here we are. Humans are observing the cosmos. This is the present. This is from 1 billion years old. Again, this is from since the Big Bang, from about 1 billion to 14, where we are now, is the era of galaxies. Stars and galaxies and clusters of galaxies are dominating the universe as we see it today. The first galaxies we think actually form at about 1 billion years, which marks the boundary of those particular regions. The era of atoms is before 1 billion years, and this is where atoms and plasmas, stars begin to form. There's a dead period. This surface here that you see, this red surface, is the surface of last scattering. That is the instant in time where the universe becomes transparent to light, and these are the photons that we're observing now as the cosmic microwave background radiation. And so before this is the instant where atoms become a thing, in the sense that they become neutral. They gather electrons, and the universe becomes transparent. Therefore, it's still too hot to form, or it takes a while to form stars. Those stars form and then begin to form early galaxies by about 1 billion years. But that surface of last scattering occurs 300 to 400 years post Big Bang. The universe has already had a long chance to cool by this point. And this is the surface of last scattering itself. You can see this is, I forgot to talk about the chart down here. This is the plot that we showed from COBE. As we move back in time, that becomes hotter and hotter. Those wavelengths become shorter and shorter, and they imply a hotter and hotter value of the temperature of the universe. And by this time, we're already up to, I don't know, hundreds of kelvins instead of single-digit kelvins at the era of atoms forming. Okay, now there's several interesting stages that the universe is going to go through, but I want to start at the beginning now and think about 10 to the negative 43 seconds after the Big Bang, right? This is where we're at 10 to the 30 something large, 10 to 35, I don't know, Kelvin. We don't understand what physics is now, right? This is question marks. This is what the physics is happening at this particular time in the universe. We don't understand it. 10 to the negative 43 seconds, we don't understand it. Now we start to understand what's going on, and we think we understand some physics that are going on once we get to 10 to the negative 43 seconds after the Big Bang. They're called the gut era. So let's talk about what gut is and why we would call it that. Okay, here we are. So to understand what we mean by GUT era, GUT is an acronym we'll talk about in a second. But this is one of the amazing accomplishments of physics of the 20th century. We have been able to explain every observation of every force that has ever been seen with one of four forces. This is an amazing accomplishment. I want you to just think about that for a second. Every single thing that happens in the universe, we can explain by one of four forces. Everything. Of course, we have already talked about three of these at some level. Gravity, of course, is very important in astronomy. On large scales, gravity plays the most important role. Even though it's the weakest, this is actually in order of strongest to weakest. It's by far the weakest. But all these other ones, the strong and the weak force, act over very short time, spatial distances. And the electromagnetic force is unimportant at large scales because the universe tends to be neutrally charged at large scales. And so gravity becomes the one that actually wins out at large distances. Anyway, that's neither here nor there. The electromagnetic force we know is the electric force, which we talked about, forces between charged particles. That also implies a magnetic force, where magnets come from and magnetic fields come from. It's actually, you can describe all those things with a single force, which is kind of cool. The strong nuclear force is the one that holds nuclei together, binds protons together to form atoms and neutrons together in the nuclei. Those are the three important ones, really important ones. We need a weak force to explain certain transitions and reactions that happen in nuclear physics experiments. Basically, neutrinos only interact, for instance, via the weak force. But that's it. We can explain everything that we've observed in the universe with one of these four forces, which is pretty cool. Now, it turns out that the theories for these are related to one another. In other words, we actually have a single theory that can explain both the electromagnetic force and the weak force. And it turns out, we call it the electroweak force, that if you go to high enough energies, the weak force becomes stronger and the electromagnetic force becomes weaker. And there comes a point where those two merge and become a single force. In fact, if you're talking about temperatures greater than 10 to the 16 or 17 Kelvin, there is no difference between the electromagnetic force and the weak force. They merge and become a single force, which is interesting. The strong force also, the electroweak force, as you go even hotter, becomes stronger. The strong force gets weaker. And there comes a point at extremely high temperatures and high energies where those will come together. And this is where the GUT thing comes in. The GUT is an acronym that means Grand Unified Theory. This is a theory that can combine the weak force, the electromagnetic force, and the strong force into a single force at very high temperatures. And this is what we refer to as the GUT era of the universe, when temperatures were hot enough and energies were high enough that all three of these forces merged into a single force, the GUT force, the Grand Unified Theory force. And so that is the era of the universe. The GUT era is from this point, temperature, and backwards to a point where we don't really understand what's going on. Now, this is the interesting thing about physics in the year 2020. We understand these three forces fairly well, and we understand gravity fairly well. Einstein's theory of gravity works very well and has never failed a test that we've given it. But these three work very nicely with quantum mechanics, say, and gravity doesn't. It's not at all clear. We think, if we go back far enough, that gravity and these four forces should all merge to form a single superforce. But we have no idea how the physics of that works. At this point in time, gravity is incompatible with these three other forces. So the big question mark here is, this is why we don't know. At 10 to the negative 43 seconds post Big Bang, the temperature is 10 to the negative 10 to the 32 Kelvin. We don't understand physics at that point. And so we can't extrapolate the curve or our knowledge of the universe back any further than that. Presumably, they're going to come together, and there will be some theory which we can come up with eventually, which combines all 4 of these into a single single force, but we're certainly not there yet. Okay, let's go back to our slider. So that explains the gut era is the era when the grand unified theory, in other words, the 3 strong, weak, and electromagnetic forces are acting as one. Back here, gravity probably is there too, but we don't understand it. And it's so hot now that, you know, protons and neutrons aren't even a thing, right? Those are made up of quarks, and it's just a quark soup at this point. It's so hot. Now, strong force becomes distinct, perhaps causing the inflation. We'll talk about inflation in a second. But these forces decoupling can, in fact, cause interesting things to happen to the universe, and inflation may be one of those events. Stay tuned. Electroweak era, the era when the electromagnetic and the weak force were combined together. These now they come at about 10 to the minus 10 seconds. They become distinct, and we have the particle era. Elementary particles, antimatter is common. Again, this is still a quark soup here. Now, the interesting thing happens at 0.001 seconds. Remember, antimatter, for every quark, there's an antiquark. For every proton, for every electron, there's a positron. In the early universe, we expect almost equal numbers of these things, and they're just sort of annihilating one another and moving back and forth. And there's so much energy that it's not a problem. Interestingly, and this is one of the mysteries of the universe, really. Why is there matter in the universe now and not antimatter? Well, almost all of those in this era, there's almost equal numbers of them. At this point, matter annihilates antimatter, and there's no longer enough matter energy in the universe to create new antimatter or matter particles. And so something like for every million particles of antimatter, there's 1,000,001 particle of matter. And so when they all collide together and annihilate one another, there's a tiny bit of extra matter left over. And that extra little bit of matter is what makes all of us, all of the stars and galaxies and everything that we see, the planets, us, is because there was a tiny bit more amount of matter than antimatter in this early part of the universe. Anyway, what I want to talk about next is the time between 0.001 seconds and 3 minutes. The era of nucleosynthesis, because this is where now the antimatter is gone. We're just talking about matter, but it is hot enough in this time that nuclear fusion can happen, similar to the interiors of stars. And so I want to talk about that now because it gives us another prediction of the Big Bang model. Great. So I'm actually going to stop this video there and talk about the first 3 minutes post Big Bang and how that nuclear fusion happens and what we expect to come out of it. So stay tuned for that.